Yeah.
Yeah. Okay.
Let's start.
Want to introduce your section? Those two slides.
Community. Yeah.
Okay. So welcome everyone. Thanks for joining us this morning. We're going to kick off this 3-hour marathon with a quick introduction to the two groups that are hosting today. The workshop title is on landslide warnings and predictions using IoT and machine learning. And the hosts today are the three scientists that you see down here. Myself, Dylan Mikesell, Luca, and Zhongqiang are both here with me at the NGI office in Oslo. We're going to facilitate 4 speakers today and then a panel discussion on this topic. So without further ado, we're going to kick it off. And I will hand it off really quick.
Yes. Hello, everyone. My name is Zhongqiang Liu. I'm the chair of ISMG TC309. Just give a very brief introduction of this technical community. So with the growing interest in machine learning and artificial intelligence, in 2018, we formed this technical community within ISMG. For those who you are not quite familiar with ISMG, ISMG is basically the International Society for Soil Mechanics and Geotechnical Engineering. So our main goal and objectives is to promote machine learning and big data analysis in geotechnical engineering by, for instance, organizing webinars as we do today. And also we provide some guidelines, state of art, state of practice. And then also we organize a series of conferences. So in this year, in late August, early September, we have our international conference on machine learning and big data in geoscience in Ireland, Cook. Until now, we have 70 members from over 30 countries. So we have been growing in the past 5 years. And I'm the chair, and we also have Mohammed as vice chair, and Dongming Zhang from Shanghai as the secretary. Next slide. Yes, so in 2019, just right after we established this technical community, we conducted an online survey. One of the questions is about machine learning applications that can, in which area we can transfer our knowledge or value for industry in the coming 10 years. And the survey highlighted that machine learning is expected to have a significant impact on monitoring and the observational method in the coming 10 years.
Sorry, Zhongqiang, to interrupt you. We don't see your slides.
Really?
Okay, now we see.
I see. Okay.
Okay, good. So basically, what I'm saying on this slide is we conducted one survey, online survey, and it highlighted that machine learning can have a significant impact on monitoring, including IoT as well. And for our workshop today, so basically, as we all know, landslide is a very complex and dynamic phenomenon and could be triggered by various environmental factors. So IoT and monitoring can be really important to detect and predict a landslide. So I am very much look forward to hearing the presentations by our 4 distinguished speakers today. And I'm hoping we could also exchange our ideas in the panel discussion and have more and more collaborations in the future. So without further delay, I think I pass
To Luca.
to Luca. Yeah.
Okay, well, welcome, and I am Luca Piciullo, and I basically want to, this is a joint workshop, so we are joining two kind of groups, the LANDAWARE group that I'm representing here today, and the Zhongqiang Technical Committee on Machine Learning. The LANDAWARE is a multidisciplinary network or communities of different individuals on landside early warning systems. The chair at the moment is Professor Michele Calvello, and these were the starting working groups that were defined since the beginning, and we recently have added a new working group that is called Working Group A8 on IoT-based methods and modeling. That is the working group that I'm chairing. What we have done so far and what's the purpose of it? The objectives are to promote the applications of innovation and sensors in the IoT, in the Internet of Things technologies. So how to use IoT for real-time monitoring, but not only that, how we can use this IoT also for using the data for modeling and real-time warning. So this is the aim, is to sharing experience in this type of field, real-time monitoring and more modeling for early warning purposes. We have, the idea is also to share case studies. We have some case studies with monitored slopes that we have data for, and we are willingness to share this data, and some others may have models or other things. So these things can be, and this arena, this working group can be a good moment and a good initiative to share these things. And what we are doing webinars, workshops at the moment. We have done 3. The first one was on seismic noise and geophysical monitoring. These were the people invited for the first workshop. We have the slides for that if you are interested to check what has been said. Then workshop 2 was about real-time monitoring strategies for landslide risk management, where 3 case studies were presented by Professor Ingieri, Armir, and Claudia Messina. In this case, we have the recording of that, and if you are interested, you can check, and you can click on the link at the bottom. And then we have done a 3rd workshop on the use of IoT data, where Ben Myrus, myself, and also Professor Greco were involved. And again, there is a YouTube link where you can watch if you missed it, this webinar. What's next? What's the timeline? So we have done 3 workshops. What's next? We have today this joint workshop with TC309. Then we are going to have another workshop 5 in March, April, I would say. Then May, we are going to be physically present at EGU. So if you are going to be at EGU, send us an email and we can arrange a physical meeting. And then we are planning for September a physical meeting of the Working Group 8 here at NGI to discuss and to first meet physically together. Last important thing, June 7th to 10th this year, we are hosting the 3rd JTC workshop on impact of global changes on landslides risk here in Oslo. So if you are interested to know more, you can check the link that is at the bottom. So just last slide, if you want to join Working Group 8 and join the LANDAWARE network, what you have to do, there are no rules. Basically, you just go on the LANDAWARE website and you register and you tick the box that about being informed of Working Group 8 activities. And this is the link of the Working Group 8. And then if it's the first time for you joining our working group, I would suggest you to take your phone, use the camera to scan this QR code and to answer some very simple questions of our questionnaire. This will help us to keep your emails, keep you informed, and to know what you are doing and how you can contribute to our working group. So thanks, and I think it's time to go forward.
Okay, so yeah, today, just a quick overview. The goal is to further our understanding of landslide monitoring and modeling. And so the theme today is landslide warning and predictions using IoT and machine learning. And I think everybody has maybe different definitions of IoT, but in the most sort of broad sense, we can define it as the evolution of the internet where computing devices, including all of these things, can be embedded into everyday objects to send and receive data. And there's now, over the last couple of years, been quite a few interesting publications looking at IoT related to landslides. And then the interesting component here is that if we have lots of these sensors now sending in semi-real-time data, we need to incorporate machine learning as a tool to start analyzing this kind of data. So that's the overarching theme for today. We put together the agenda, so I'm sure everybody has seen that, but here's the plan. In 5 minutes, the folks in Oslo are going to shut up, and we're going to have 4 speakers talking in groups of 2. So we'll take a bathroom break in the middle. And then after the 4 speakers are done, we're going to ask all 4 to come back, and we'll have a panel discussion, and then Luca will make some closing remarks. So I'm going to give a quick introduction to these 4 speakers, and then we'll get going. So we have Professor Yu-Hsing. He's a professor in the Department of Civil Engineering and Civil and Environmental Engineering in Hong Kong at the University of Science and Technology. He's also the Associate Dean of the School of Engineering, and he has a PhD in Civil Engineering from Georgia Tech and has multiple international awards and is a fellow of the ASCE and HKIE. He's going to start off. He's going to be followed by Dr. Emir Oguz. Emir is a researcher at NGI. You will notice he's online and not in the office here in Oslo because he's in Trondheim. But he works in the Geotechnics and Natural Hazards Department as a researcher. He got his PhD from NTNU, which is the Norwegian Technical University in Trondheim, in physics-based landslide modeling. And he's been incorporating IoT-based monitoring into early warning strategies recently. So we're going to hear a bit about that today. Our third speaker is Dr. Marianna Pirone. Marianna is an associate professor of geotechnics at the University of Naples Federico II. She also got her PhD there in geotechnical engineering. And her past research has been over a broad view of things, but largely saturated and unsaturated soil mechanics and numerical modeling applied to slope scale, let's say landslides and flows. And so the more recent work that is applicable to what we're talking about today is prototyping of measurements and measurement factors related to flows and triggering. So we'll hear something about that today. And our last speaker is going to be Dr. Konstantinos Marios Angelopoulos. Hope I said that right. And Marios is also an associate professor at Bournemouth University in the UK in networked and sensing systems. And he leads the Bournemouth University IoT lab. So lots of experience with IoT, and he's also a founding member of the Future and Complex Networks Research Group, FlexNet. He's started 3 MS courses in IoT, so well-versed in this. He could probably refine our definition that we put up there in the beginning. But he also then serves on some interesting committees, and one that I'll point out is just this International Telecommunication Union as an associate rapporteur of question 5, which covers research in emerging technologies, terminology, and definitions in what they call SG8, which is, or sorry, not SG8, we're working group 8, SG20, so study group 20, which focuses on the Internet of Things and smart cities and communities. So we have a nice group of speakers with diverse backgrounds today that are going to share their knowledge of IoT and machine learning. I will hand it over to Yu-Hsing, and hope everyone enjoys today. We'll take a bathroom break or a bio break at 10:10.
Okay, thank you very much for the invitation. Let me share my screen. Can everyone see my screen? Yes, okay.
Yes.
Okay, perfect. Okay, so today's topic is indeed very difficult, landslide warning and the prediction. So I begin to think about how to make this presentation. So I will try to use a different way. The goal is to lead to fruitful and meaningful discussion later on. So my name is Wang Chuan from Design Lab, HKUST. So what is DESR Lab? Basically, it is a data-enabled, scalable research laboratory. Just by the name, you know, data is very important. So data indeed is a key for many things. And then this design lab, when I established this lab, is starting from a makerspace. So basically, we have a student, faculty coming from different departments. We join together to do multidisciplinary research. So the goal for this lab is very simple. We want to innovate fundamental smart city infrastructural technologies to connect citizens and the decision making. We also work closely with government department and also industrial partners. Throughout those collaboration, we realize a fact. Smart city is not all about money, although money is very important, but smart city is about integration. So we propose the vertical AI as an integrated solution. We start from sensor design, then begin to collect data, then collect a lot of data, become big data. We have to rely on AI, basically deep learning, to help us analyze the data and make a good decision. However, if we think about the future, it's not only the integration for this circle, it's a higher level integration, which is human robot AI partnership. If we look at the evolution of robotics, in the early time, we asked the robot to help us do something, observe something. So now we can give the robot an AI brain, and then the robot can begin to think, even interact with the environment. So this is a robot dog in our lab, and Hong Kong GEO also purchased a robot dog to help them to do the survey. So if you have a chance to look at the YouTube published Google robot butler or in the Tesla AI Day, they say they're going to have a humanoid robot. You probably will agree with me. Sooner or later, we are going to have robot colleague. Indeed, now we have already. So in the following, I will use a landslide as one example to talk about what is the integrated solution. Let's start from the sensor design. So following the traditional sensing matrix, we have a dynamic measurement. We call IoT the sensor. We also have sensor for steady monitoring. Start from the dynamic one. We call GeoIoT. Basically, we just give you a very fancy name, Internet of Things in geotechnical engineering. And this is a sensor we install on the retaining wall at the landslide prone area, Lushan, Taiwan. And later we'll talk about this case. So if we look at this sensor, basically we have a control module, sensor module, we have GPS antenna, we have solar panel with a car battery as a power supply. If we look at the control panel, we have a Raspberry Pi, a single board computer as a brand for the sensor. And we also have a tailor-made system monitor layer, power supply, regulator, GPS receiver, and then also different kind of telemetry option. Also is a data logger. And then for the sensor module, we can put any kind of sensor. So basically, the purpose for me is not to show off, oh, this is how powerful this sensor. I think the key point is people always ask me, as a geotechnical engineer, why you want to spend such an effort to make a sensor by yourself? The answer to me is always, I also want to buy one, but I cannot buy one in the market because we have a special requirement. This is a Sichuan, China, and this is real snow. And this is my student, is a real student. I sent him there, he need to finish job, otherwise he cannot graduate, poor student. And then the sensor there in the harsh environment, the sensor also finish the job, get the data and send it back. So we need to have a very high fault tolerance. And how to achieve this goal is achieved by design. So for example, we have full protection of power supply, we have surge protection, etc. And then in addition to that, we have redundant sensors. If one sensor become malfunctional, we have another one, make sure we can get the data. And then also, we have a redundant storage. What does that mean? Sometimes the telemetry option may not work. We need to temporarily store the data. And then whenever the wireless transmission resumes, we send the data back. We also need to consider a different way to fix the problem if there's any malfunction condition. So this is a real example. You can see this our sensor. This is a sensor installed by another contractor. This is the entire cemetery, Hong Kong. So after wildfire, our sensor still survive. You can see their sensors are completely destroyed. And in addition to that, we also need to consider everything is over the air, because I cannot send my student back to the site quite often. It's in the remote area. So we need to make everything over the air, upgrade the sensor, the software, and also fix the problem, etc. We also need to consider flexibility. What does that mean? If we look at the market, every season you are going to have one new sensor. So whenever a new sensor comes into the market, we just take out the old one and then replace a new one without changing the whole architecture of the sensor. We also need to consider the flexible installation. We install the sensor on a tree, on a column, even buried on the ground. Okay, when we start this project, we are very ambitious. We want to make it really push the sensor limit. And we make it always on, has a very high frequency, up to 690 Hertz. We don't want to miss any signal. Okay, I'll tell you the purpose later. And now it's 8th generation. So basically you can function as a motion sensor and also like a seismic sensor. We compare with traditional seismometer, and then it works quite well. And also has a GPS function, so you can get the displacement. Because it's in-house made, so we can make it very compatible to different satellite systems. Okay, now let's look at performance. And this project will also collaborate with another Professor Wang from National Jinan University, Taiwan. And the monitoring site is Lushan and the Songmao, Taiwan. So taking Lushan is one example. So you can see this landslide prone area is huge. And then you can look at the bottom, is abandoned hotel. When I was young, this is a very famous tourist spot for the hot spring. So now it's completely abandoned after those hotels were destroyed by debris flow. So in Taiwan, we have earthquake, a lot of earthquake. It's more than 1,000 earthquake per year. And then just taking the earthquake at Hualien February 6 to 2018 is one example. There were 98 times of aftershock. We don't like earthquake, but when earthquake comes, we should make the best use of it. So we consider when earthquake comes, check the slope. It is a field scale, non-destructive measurement. Then you can imagine the slope will towards to a particular direction, have a higher movement, which is corresponding to the sliding direction. So we call directivity. So we use a monitoring point 3 as one example to look at the performance. So this is the record done by the seismic station by the Central Weather Bureau, Taiwan. And the wave sensor one is very expensive one, military grade. And the other one is just the one in your iPhone. And then you can look at the result is pretty much similar. And then we can use HVSR to get directivity. We can know which direction is a favorite moving direction for the slope. And then also compare with the borehole inclinometer, it's quite close. So yeah, we can basically use the sensor and use HVSR to get a sliding direction. We also process data from more than 200 earthquakes, and then we realize the directivity is independent to the location of epicenter and also the peak ground acceleration, the bubble size. And then especially there's a landslide event before and after they are the same as expected. Now we want to look at this landslide event in June 2017. So the main rainfall is from June 3rd to June 4th. And then we can look at the displacement measured by the GPS receiver. So starting from May, and then in the June 3rd and the June 4th, we can see the displacement. And even the rainfall stop, we can continuously measure the displacement. and it is also quite close to the measurement by the total station after the event. So based on that, we can issue the warning for the ongoing landslide. However, it is not really complete my goal. I will tell you later as well. So we also understand after the rainfall, as I mentioned, we continue to measure the movement. It is because there's a very slow groundwater drawdown. So that will promote the slow movement even the rainfall stop. Okay, in order to complete the story, I also want to mention about the steady monitoring using LoRa. So a lot of people talking about how to get the data from the existing device. When we talk about smart city applications, we call crowd, same thing. And people think LoRa, the low power wide area networking, might be a good solution. We haven't done anything using LoRa for landslide, but we have done this for the tree. So you can just using consider landslide as a tree because the consideration is the same. That's a key point I want to make. I want to talk about today. What is the key concern when we use LoRa? Okay, so basically for the trees in the remote area, like a landslide, and they are not close. So it's hard for us to use a traditional sensing network based on the coast. It's also difficult for us to put the same car on each tree. Otherwise, it will be very, very expensive. So LoRa will be a good choice. Let me explain more. So this is the whole system. We have a sensor on the tree. You can consider we have sensor on the landslide. Then there's a gateway, and we have server, the data center, including network and the application servers. So for the sensor, we put a main sensor inside. And this is a gateway in the campus. And then we have very beautiful campus. I can see sunrise every morning. You're welcome to visit us. So this is the gateway in the campus. We put a sensor in the Jiansha area in the city. Although we don't have high mountain in Hong Kong, but we do have a high-rise building in the city. And we can get a very good signal, even though the distance is about 11 kilometers. It's pretty wide. Okay, so LoRa using the chirp up, chirp down as a coding. So it's a very spatial signal, just like a bird chirping. So birds singing in the forest, right? So they don't need to shout because it's a very spatial sound. So the same species bird can hear that. So similar to the sensor doesn't need to shout. So the power can be saved. So the purpose for us is we can have a battery last for months, even years, depends on how often we want the data to be transmitted. So because it's a wide area, so basically we just install like a 20 to 19 gateway, the signal is able to cover the entire Hong Kong. In the operation frequency, every country is different. In Hong Kong, the free range is 920, 925 megahertz. Okay, so here comes to the key point. People ask me why we just subscribe the commercial plan. But indeed, we cannot because we have a spatial situation. We have to ask ourselves, when do we need to get a signal? It's whenever the warning issued by the Hong Kong Observatory. That's when the bad weather comes, typhoon, heavy rain, strong wind, etc. So when the bad weather comes, every sensor wants to talk. The gateway will hear nothing. Why? It's because like you go to the big stadium, when the team you suppose win the game, you want to make a phone call to your friend to share your happiness, but physically you cannot because the line is jammed. So similar to the same situation, when every sensor talks, the gateway will be in trouble. So we need to have a very special make layer to control who should talk first, who should talk to again. If the gateway didn't get a response from a sensor, we need to ask the sensor to talk again. All those need to have two-way communication. And when you subscribe commercial plan, it doesn't allow you to do so. Okay, then let's look at the performance during the super typhoon Manku, one of the strongest one in Hong Kong history. So this is the next day, the campus is like an abandoned one, and the many trees fall down, and some small structure also fall down. So my first mission is to look at, okay, whether or not the gateway is still there, doesn't fly away to kill someone. Fortunately, the gateway physically survived. Also, you can look at the transmission signal. It's also very good. even during the bad weather. And then, but the most important thing is we want a sensor, but we want a sensor to capture the physics or the underlying mechanics involved in the whole process, no matter it's a landslide or tree fall down. So we can look at, so this is more like a straight strain response. At the very beginning, it's just an elastic response, then become elastoplastic, and then finally accelerate the plastic formation and then fall down in a particular direction. So the key point is we want a sensor is able to capture the underlying physics. So this is a potential application. In Hong Kong, we have a lot of flexible barrier. So we need to know whenever the debris hits the barrier, we need to go clean up. The typhoon, super typhoon Manku, also top down several poles, but nobody knows until we go there to check. So if we have a sensor on the pole, we can know, oh, the pole is fall down. We need to have this problem fixed. However, this is in the remote area. We cannot go there quite often. So we want the sensor can last longer. Battery can last for months, even years. And LoRa will be a good choice. Okay, then I'll talk about data collection. I just want to talk about one key point. For loss monitoring, time is very important. So the sensor we put on landslide monitoring, because we have GPS, so we are able to synchronize the time with a Stratton 0 clock every minute. In addition to that, we consider security issue. Nobody can hack into the sensor. Also consider different kind of security issue. Okay. So then we talk about big data. This is typically people ignore this part, but it's very important. Let's talk about the data center in our lab. So we use Cassandra as a data storage, like Facebook did. We use a Spark to processing the data. Okay, just say in short, in addition to have a scalable storage capability, what does that mean? That means whenever the hard disk is full, we just plug in a new hard disk without changing the whole system. In addition to that, we need to have a very good filing system because we want to retrieve the file in a fast way, especially when we do the time series data analysis. Sometimes we need to get a huge amount of data at the same time. Okay. In addition to that, the data center needs to support AI training, computation, and also data visualization. Back-end infrastructure is very important, but we typically ignore it. Without this infrastructure, it's very difficult for us to do anything. In addition to that, computational is not cheap, especially when we train the deep learning model. So let's talk about deep learning. So after AlphaGo win again, now you ask a year one student, what will be your major? Everyone wants to study CS. Used to be civil in the past in Hong Kong, but now it's CS. Computer used to be programmable, now it become teachable. So we teach the model, AI model, help us to process time series data in the time domain or in the time frequency domain, or 2D image data, and also the 3D point cloud data. And today, I will only focus on the time series data and the 2D image data. Go back to the case, we put a sensor at the Lushan. So we have high frequency sampling. So if a lot of data coming in a minute, so whenever the data come, we first of all, we use an autoencoder to make a judgment whether it is anomaly or not. If it's an abnormal signal, then we use a supervised learning to make a judgment. There's a car passing by, there's an earthquake, or it's a real landslide. Sometimes they cannot make a judgment. So we send the data to the domain expert to help to improve the model. Okay, however, as I mentioned, I didn't really achieve the goal because what I want is not for the landslide already happened. We always want to get early warning. So when I start this project, it's quite crazy. I think, okay, I can design a sensor like a small dust or small soil particle. I just sprayed it on the slope. I don't want to drill a hole because whenever you drill a hole, it will be quite difficult and quite expensive. So we have a lot of small sensor on the slope. Whenever the slope has any signal, that's why I use a very high frequency sampling frequency. I want to capture any precursor signal before the main event. However, I haven't done it. We have tried so hard using AI to help us to analyze all the data, but it's still not that easy because too many noises. Hopefully someday we can do it. Maybe we can share the idea later. The other thing we did is for using deep learning for landslide inventory mapping. So in the past, for the historical landslide, we always need to have this inventory. So we just use a human expert to do it maybe in several months. So now the idea is, can we train the deep learning model and then do the mapping automatically? So this is the training we have. Basically, we give the data before, after landslide, and also the DTM. This is very important. I'll mention the effect, and also the label data. And then we go through the normal process. You know, we have data augmentation, we do the training, validation, testing. But here, we do the pixel level segmentation down to the 0.5 meter. And then for this project, although we use the aerial photo, but you can use a satellite image with high resolution, you will achieve the same goal. So let's look at the result. This is done by the human expert, this is by the deep learning. You can see it's pretty good. And also we can compare the classical machine learning method because it's down to the pixel level, so it's more continuous. And in addition to that, even some hidden area, the machine learning model, this deep learning model, okay, can do a very good job. So now I want to show you one thing. If you look at the color, the seashore area is very similar to landslide area. So if we only train a model using the area photo without the digital terrain data, the model will make mistake. However, after we train the model with the digital terrain data, the model is okay. So that tells us, deep learning model, you can feed any user information as you wish. Then we can improve the prediction accuracy. So follow the same idea, we can zoom into a small area at the Lantau Island, Hong Kong. We do the multi-class classification. The deep learning model can help us identify where are the buildings and where are the landslides. And then we can impose digital terrain data. So we can have basic idea to make a simple risk analysis, where the danger is, where it's not. Also the direction for the landslide. So now we can extend the whole analysis to the entire Lantau Island. You will take probably 20 to 30 minutes, depends on your computational power. Then we're able to do it again. Where are the houses, the buildings, the road, as well as the landslide. Then we can export the data to the GIS for different kinds of application. Okay, so sometimes we publish paper, we say, oh, the model have high accuracy, and then we publish it. But indeed, it's not the end of the story. That's exactly the beginning of all the challenges. Because we all know that for the deep learning model, it's going to, the accuracy, prediction accuracy, going to change with time and also with places. Okay, so we need to involve uncertainty for the model prediction. We need to know when the model and under what kind of condition the model cannot perform very well. Because you probably have an answer for yourself. If I change the places, I say, okay, I just do the fine tuning or retrain the model. But the key point is, how are you going to do the fine tuning and even retrain the model? When? What will be the efficient way? Because the labeling is not cheap at all. Although we ask a PG student, but in reality, labeling is not a cheap task. So we can compare the result and also uncertainty map. So we can know where the AI model, the deep learning model has a concern. The model is not sure whether it's a landslide or just a concrete structure there. Then we can ask the human expert to make a judgment. So indeed, we want a human to be in the loop all the time, starting from labeling all the way to finish the training of a model. Domain knowledge is still very important. Okay, this is another case. The AI model, we get confused about this landslide and the seashore connection area. Okay, so with uncertainty, we can know what exactly the part the AI model cannot predict well. So we can target to the weakness part and train the model in an efficient way to help with accurate learning. We also can know when the uncertainty becomes higher, then it will help us to know, okay, it's time for us to fine tune, even retrain the model in the long run, which is continuous learning. Okay, after we have a good model, we can burn into a chips, or we can design AI chips, we put on the UAV. So whenever necessary, we just fly, and then the UAV can process data at the edge and transmit data back. Haven't done it, but that was my dream. Okay, indeed, I have more concerns. The biggest news in the education circle last week is University of Hong Kong temporarily banned students from using ChatGPT. Now it's so popular, and the other AI-based tool for coursework. Is it right to do that, or is it too late? But anyhow, we need to have some regulation. We need to have some regulation for ethical AI, for responsible AI. What does that mean? So if Google has a machine learning model, it can do the foundation design. Do we need to give a certificate, just like a Korean Chess Institute give a certificate to AlphaGo? In Hong Kong IE, we give the IR title for those charter engineer, professional engineer. Should we give an IR title to AI? So indeed, we have more things we need to concern: accountability, responsibility, transparency. So is AI model the accuracy trustable? What would be the accuracy change with time and places? And if AI model make a mistake, you say, okay, AI predict landslide is going to happen, and this didn't happen, or it's the opposite, and finally have some casualty, cause some casualty and then property loss. Who is going to take responsibility? And then we also know for deep learning model, even though you use exactly the same model, however, if the training data set is different, the performance will also be different. But you look at the civil engineering, we don't have benchmarking data like a CS Word. They have those benchmarking data for everyone to test the model, but for civil, we don't. We need to have that. In any way, that GEO probably, in Hong Kong, GEO probably different guide for engineering application, but we also need to have a guide to help us to work together, human, robot, AI partnership. So in the end, we can just ask robot AI to do those tedious work, finish the measurement, finish the data processing, and then human beings still do the final decision making. With this partnership in a healthy way, we are able to see things that we should have seen before and make a better decision. Okay, thank you very much, and hopefully we can have a fruitful discussion later on. Thank you.
Thank you, Professor Wang. Okay, we will move on to Emir.
You can mention that we can have questions at the end of the workshop, where we have a dedicated time for questions and comments and discussion in general.
You're muted, Emir.
Do you see the presentation, Luca?
Yes.
Yes.
Oh, okay, amazing. So thank you, Professor Wang, for your presentation. So now I would like to present my PhD work, one part of my PhD work on IoT-based hydrological monitoring and water-induced landslides. Mainly, I will go through a case study in central Norway, and I will mention which early warning strategies that we have considered in the study. This is the content of today's presentation. I will first introduce the study area, then I will go through the IoT-based hydrological monitoring system that we have deployed in this study area. I will show you the system deployment, the overall IoT concept that we deployed, and some observations. Then later on, I will mention about the early warning model strategies, and I will conclude my presentation with certain major conclusions. This PhD work was done at Norwegian University of Science and Technology in Klima Digital project. So this project aims to reduce the social risks imposed by geohazards in a changing climate with a geohazard assessment framework. So in this concept, what we mean by IoT is a concept of interacting with physical world through a network of natural or man-made objects that are connected to internet and process the collected data automatically without need for human intervention. So this figure is the overall framework of the Klima Digital project. So here we have a case study area where we have, which is prone to landslide. And we have many sensors which are collecting data which is related to landslide initiations such as rainfall, volumetric water content, suction, and others. And the data is transferred to a cloud-based system. In this cloud-based system, you might store the data or you can even process it locally and send it to a geohazard assessment framework. In addition to that, there is also a climate model in which we collect the weather forecasts and climate predictions for the study area so that we can integrate both the data from the field and the climate model into one geohazard assessment framework to predict the landslide events. The current study includes the implementation and the deployment of the landslide monitoring system supported by IoT in a landslide-prone area, interpretation of the collected data, and integration of the data into a physical-based landslide prediction model to have a certain landslide early warning system. I will first start with the study area. So this study area was selected through multiple site selection criteria. The first one is location. So we decided to have up to 2-hour drive from Trondheim center. So, and this is the map which shows the driving time from Trondheim center, which is lower than 2 hours. It should be easily accessible. It should be near a road or path for the monitoring purpose. So it should be above the marine limit, which is approximately 180 meters in Trondheim region. And there should be some shallow landslide events, warnings, or initiation signs in the proximity of the landslide monitoring point. With respect to geometry and field conditions, we should have relatively steep slopes, which is above 25 degrees, and depth to bedrock is 2-3 meters is what we have wanted. We had multiple maps, so this is the heat map of landslide events, which are registered to landslide database in Norway. And we had also some weather stations just with a buffer zone of 10 kilometers. Although we have installed a weather station, having more weather station is always better. So we had multiple of these site selection criteria, and we end up with a catchment area between Hegra and Meråkerstiz in Trøndelag region, which is almost, this catchment area is almost 200 square kilometers. Then when it comes to selection of the monitoring points, we had 18 potential case study location points in the study area, and we had site visit to decide where to place the monitoring points. So then we also had some trial pits to investigate the soil stratigraphy and also to get the strength parameters and so on. At the end, we decided 2 locations in this study area, which is also shown in this figure. So one is in the fluvial deposit, and one is in moraine type of soil. So if we look at the locations in detail, in both locations we have water channels. And due to the presence of water channels, we decided to place 2 monitoring points at both sides of the water channel at different different heights. In both, we have 2 monitoring points and trial pits at both, and we have a weather station in location 1. This is the location 1, and this is the location 2. Here you see the stratigraphy and the placement of the sensors. This is the end phase of the monitoring point, D12, and this is the weather station that we have used from meter group. And this is location 2, where it's quite shallow, like depth to bedrock is 1 to 1.5 meter, so we couldn't dig more than 1 meter. So therefore, these are the piezometers that we have used. We couldn't place them in location 2. So these are some pictures from the sensor placements. So we did it manually ourselves with shovels and augers to dig, and yeah, it was quite tough. So this is one monitoring point in location 1. Here we have a monitoring point. Here you see the stratigraphy of that specific point. We have 3 suction sensors and 3 volumetric water content sensors, which were placed at 0.3, 0.5, and 0.9 meter depths. And we used 2 piezometers at approximately 1.4 and 2.2 meter depths. And we used sand in the proximity of the piezometers, and we also used bentonite at the top of the sand layer to prevent water passage through this stratigraphy vertically. The cables are going through this trench and connected to this IoT device, which transfers the data through this PVC pipe. These are some pictures from the placement of the sensors. Here I will show you some of the collected data from this specific monitoring point. Here we have volumetric water content and suction sensors. And here on the x-axis, you see date from 2020 to 2022, almost 2-year data that we have. And we have distinguished different responses of the soil depending on the time. So between August and December and March to April, we have observed very high volumetric water content values with almost no substantial suction value. This means that the soil was almost saturated in these time periods in the study area. When it comes to December to March, we observed that the volumetric water content values at 0.3 meter depth showed a sudden decrease, and at the same time, the suction values at the same depth showed a sudden increase. It was interpreted to the fact that the ground at 0.3 meter depth was frozen in this time period. And this frozen ground was frozen until the beginning of March when the air temperature starts increasing. As air temperature increase, the ground starts thawing, and we have sudden increase in the volumetric water content and sudden decrease in the suction. Another time interval is March to August in this Trøndelag region, where we have high air temperature, and due to that we have a trend of decreasing volumetric water content by time. Although we have some rainfall events which increase the volumetric water content, the general trend is decrease. Similarly, we have suction values which goes up to 100 kilopascal. At some other points, it goes up to the limits of the sensor. So how are we going to utilize this data in this early warning system? So this is the overall concept of the IoT-based hydrological monitoring of water-induced landslides in this current study. We have a device layer. So we divided it into 5 different layers: device, network, platform, application, and user. So the device layer includes IoT devices, which are providing sensing, actuating, controlling, and monitoring activities. And the data is these figures are these 2 are the IoT device that we have used. Here the box includes the all IoT technology, and we have batteries, and we just connect the sensors from the bottom. And this is the weather station that we have used from Meter Group. In the network layer, as the Professor Wang says, we have used low power wide area networks. So there are different technologies in this market. So these are like LoRa, Sigfox, MB-IoT, and some others. And the technology is further evolving quite fast. So in this study, we have used MB-IoT and LTE-M technologies to transfer the data from devices to the platform layer, which which was found quite satisfactory in the study. The Platform layer includes data storage or basic processing. It is associated with the cloud services. So it might be infrastructure as a service or software as a service, which gives access over the web for data processing. When it comes to application, you might use the data in different ways. So you can have, in this layer, you might have like landslide prediction models and early warning systems to support landslide risk assessment systems. And for the application, you might follow different early warning strategies. It might be very simple sensor-based warning systems. It might be empirical-based warning systems, or it might be physical-based warning systems. So it might also be artificial intelligence, deep learning. So you may use any application in the application layer to relate the data or observation to the landslide predictions so that you can push the data to the user side to mitigate the risk. Before going into further details of the landslide warning strategies, I will just briefly mention about the performance of the system implemented. So I found it quite satisfactory, the performance of the system, because we only had just few issues with that. So just once the IoT device didn't start after installation, but we replaced it. And the weather station was not recording the data for 2 weeks, I guess, yeah, 2 weeks. And we found that it's just due to a loose connection, cable connection. And device 1 needed to be restarted to one of the IoT devices. So apart from these, we didn't have any problem in this IoT system. Not in the paper, but in the project, we have considered different strategies that I mentioned before, data-driven, empirical-based, or physical-based. If I mention them very briefly, so a sensor-based warning system is the most basic system which might be implemented based on the data. Here you see the IoT device, suction sensors and volumetric water content sensors placed at a shallow depth and piezometers at a deep. So let's assume that we are considering the volumetric water content data. We might have different levels of warning. So level 0 might be that all volumetric water content sensors have a volumetric water content of less than 90%. And you have green warning level. It might be that the shallowest volumetric water content sensors start giving volumetric water content values greater than 90%. Then in that case, you might issue yellow warning, or it might be that top 2 sensors gives volumetric water content greater than 90, then it's orange. Then if all of them gives very high volumetric water contents, then it might be red. Of course, this is quite basic and it has many limitations. So it has lack of predictive capacity due to reliance on already observed sensor values. Lack of redundancy in the alerts due to reliance on a single sensor and single data. So there is static information that are not being updated to account for varying temporal and spatial scales is another limitations. Possibility for multiple and inconsistent warning in case of using only one data. Lack of capacity to account for other geotechnical, hydrological, meteorological parameters, physics involved, and vulnerability to sensors and alert manipulations. Another early warning strategies might be empirical-based warning systems. So warning systems deployed by NVE, which is the Norwegian Water and Energy Directorate in Norway. This is based on historical landslide events and the values of relative water supply and relative degree of saturation. This is the figure which shows the early warning strategies used in Norway. So here x-axis shows degree of saturation, y-axis shows relative water supply. Relative water supply is calculated as daily rainfall divided by the mean annual rainfall during the last 30 years. And x-axis is degree of saturation, which is the estimated value from the volumetric water content sensors. There are many dots. These are the landslide events registered in the data set, and based on they tested different parameters, and the best performance was obtained by these two parameters. And there exist 4 levels of warning: red, orange, yellow, and green. Sensor data and MV system were used to demonstrate how we can use the empirical-based warning systems in this study. So, and for the degree of saturation, we took the average of 3 volumetric water content sensors at a single location. And the relative water supply was calculated based on the rainfall measurements on the nearby weather station. And we have reached level 2 warnings only during the monitoring time because there were no landslides even registered in the system, which seems to be okay. But of course, this system should be another empirical-based warning system, which would be more reliable in the for that specific site should be used. So what we have, we have some advantages and disadvantages of using empirical-based warning system. This will provide us predictive capacity, which is quite nice. Increased redundancy through the use of several data sources and historical data is also an advantage. It is possible to account for geotechnical, hydrological, and certain geotechnical parameters depending on the empirical system that you are using. And it's increased reliability in alerts due to training on historical events. These are the possibilities this system provides. Of course, it suffers from it might be very simple or crude models with limited number of model parameters. It might be either very complex with high dimensional so that it will not be interpretable to humans, or and it requires model training and also requires large training and testing data sets. The last early warning strategy that I will share is physical-based warning systems that was implemented actually as a pilot study. So here you see the web page that we designed to provide the warning system, warnings to the user. So at the bottom you see the data that was collected from the field. And here you see the study area with different colors, and those colors are representing the factor of safety values. If it is lower than 1, it is red. From 1 to 2, it is yellow, and above 2 is green color. And we have predictions at 3 time periods, 0, 24, and 48 hours from now on. So it predicts the future landslide events. How it does is first it accesses sensor data, and we have used the volumetric water content readings to calibrate the model, physical-based model that we are using. In this model, we only updated the initial groundwater conditions, and then we also obtained the weather forecast, and we have extracted hourly predictions of precipitation. Then it performs the landslide prediction analysis for the following 48 hours and provides the landslide predictions at 0, 24, and 48 hours to the online dashboard so that we send it to the user layer of the system. So this is pretty much all. So we have 2 main conclusions from this study. So especially for Norway, where we have seasonally cold climates, it's quite important to understand the hydrological response of the slopes to predict the landslides and to understand the landslide triggering conditions. And also this landslide monitoring system have very high potential to provide relevant information, which can be used in data-driven, physical-based models, artificial intelligence to estimate reliable landslide hazard. And this was shown through this pilot study and this in this research. Yeah, thank you for listening.
Great, thank you, Emir. Right on time. So
yeah,
great. I'll just put the schedule back up. So we'll take a 10-minute break and see everybody back here 20 minutes after the hour.
No,
No,
yeah,
you
yeah,
wanna
it's,
say
no,
something?
it's no, it's just yeah, mistake. Yeah.
Okay.
Okay, welcome back, everybody. Hope you had a chance to take a break. Our next speaker will be Marianna. So please share your slides.
Okay. So can I start?
Yes, please.
Okay. Can you see my screen?
Yes, we can. Go ahead, please. Yep.
Okay. So good morning to everybody, and thank you for inviting us to present in this workshop. My presentation deals with an early warning procedure based on short-time weather forecasting and numerical slope analysis. I'm carried out this work with Professor Urciuoli and Professor Picarelli. So the goal is to set up an early warning system for flow-like landslides and pyroclastic soils. It's well known that this type of phenomena are distinguished in the flow slides, debris flow, and debris avalanche according to the material involved and the paths followed along the slope. These phenomena are very dangerous, so because these are very fast, so it's very important to predict on time their triggering. There are the typical features of this phenomena. For example, the sliding mass is composed of pyroclastic deposits laying on intact or fractured bedrock. The cover is often partially saturated. This means that there is a matrix action that provides an apparent cohesion. The predisposing factors of these phenomena are the hydraulic condition before the critical events and the local geomorphological factors. Rainwater infiltration is the main triggering factor by saturating the cover, by cancelling out the apparent cohesion. So, in light of these features, hydraulic slope behavior is the key factor to predict on time the triggering of these landslides. Unfortunately, Campania region is often hit by these phenomena. In fact, in this slide, there are the events of Sarno, of Nocera Inferiore, of Ischia, in Cervinara, and this table contains main killer flow-like landslides in Campania region. It's impressive the number of victims. For example, the events of Sarno provide 159 victims. So the most common method to reduce the risk related to this landslide is early warning system. Rainfall thresholds are usually implemented in this system. There are empirical rainfall thresholds. These curves are expressed in terms of rainfall intensity and duration, and are carried out according to the rainfall that caused the past landslides. This approach may suffer from false alarms because it neglects the physical process into the slope, because this disregards the rule of a geomorphological context which the landslides occur, and because neglects the hydraulic condition before the events. There are also the physical based rainfall thresholds. Again, these curves are usually expressed in terms of rainfall intensity and duration. This time, these curves are carried out by modeling the hydraulic mechanical slope behavior via finite element method. In fact, in these slides, there are the curves obtained by modeling a slope monitored at the municipality of Monteforte Irpino in southern Italy, located close to ancient debris flows. With this approach takes in account the geomorphological context where the landslides occur, and can take into account the rule of hydraulic condition before the critical events. Then, the on-time prediction represents an alternative to rainfall thresholds. So we propose an approach based on short-time weather forecasting and numerical slope analysis. So I will show the first results, the preliminary results carried out by applying this approach. So this approach is effective at the scale of slope. So for the high-risk slopes, the slopes that insist on highway, railway, or dense urban area, the first step is to select test sites where geotechnical soil characterization has to be carried out. In terms, of course, of mechanical and hydraulic properties. Then the sensors able to measure matrix action and volumetric water content that represent the predisposing factors of this phenomena have to be installed at site. The second step is to set up a numerical modeling devoted to simulate and predict the hydraulic slope behavior. This model has to be calibrated on geotechnical soil characterization and has to validate against the field data. Once validated, this model can run to predict the hydraulic slope behavior under rainfall forecast 1 day or 2 days before. Hydraulic variables can be uploaded in simple method like, for example, limit equilibrium method to have information about safety factor in advance. It's important to highlight that this approach can suffer from 3 levels of uncertainties. The first level of uncertainties is related, of course, to weather forecasting. We have not yet faced with this issue. We think to exploit this issue by addressing an atmospheric physicist. The second level of uncertainty is related to accuracy of field readings. The third level of uncertainties is related to the model, so geotechnical soil characterization and its constraints, and also the governing equation that the code solves. So we attempt to use this approach at a test site instrumented at the municipality of Nocera Inferiore, close to past debris flows. And we try to couple the weather forecasting from 3B Meteo to an hydraulic slope modeling carried out by using SIPW and SOPW. So now I will show the first results. Let's start with a brief description of the test site. The test site is located at the Lattari Mountains, often hit by flow-like landslides. This test site was studied and instrumented within the regional project GRISIS, led by geologists of our department, Professor Santo and Dr. Forte. This test site is located close to ancient debris flows, is at height of 125 meters above sea level, is upslope E3 highway, and thanks to a lot of stratigraphic logs and 2-meter depth pyroclastic cover belonging to 79 Annus Domini eruption was recognized. Bottom upward there is a silty sand named here C1. Then there is a layer silty sand rich in palms named as A2, and then there is the top layer composed of vegetated ashy soil with a thickness of 0.5 meters. The ground science distribution of these layers are contained in the envelope of ground size distribution determined for the a lot of soils sampled at Lattari Mountains. So it's reasonable to extend the hydromechanical properties of the soils studied at Monte Faito test site, far from 20 kilometers from Nocera Inferiore, to this test site. In addition, it's well known in literature that the pyroclastic soils of Campania region showed similar friction angle at critical states because are very homogeneous toward the mechanical behavior at least. These soils are very porous. The porosity goes from 0.7 to 0.6 more or less. About the instrumentation, also the instrumentation was done within the regional project GRISIS that I have mentioned before. We installed 4 traditional tensiometers along with 4 sensors for measuring indirectly matrix action, volumetric water content at the same depth, at 0.3 meter, 0.6, 0.9, and 1.25 meter from soil surface. In addition, we installed a TDR multi-level probe and also a meteorological station. So, as instruments, as reference instruments, we installed in particular 4 traditional tensiometer, Tensio UGT, that give back direct measurements of the course of a matrix action. Accuracy is more or less 0.2 kilopascal. Maintenance is necessary because of the saturation of these instruments. Soil View 10 was installed. It is an TDR soil multi-level probe. So the advantage is to monitoring a lot of measurements of volumetric water content along the same vertical. Accuracy is more or less 0.015. Then we installed also cheaper sensors as watermark and decagon sensors. Watermark sensor use a porous stone as a measuring sensor. In particular, they give back an indirect measurements of matrix action. The calibration is very important to have reliable measurements. No maintenance is required, and there are very low costs respect to the traditional tensiometer. Decagon sensors measure as TDR probes the electric constants, but are based on capacitance technology. Their calibration, once again, is very important for high accuracy of the measurements, and also these sensors are low cost. Here there is pictures of a meteorological station installed site, and also all the sensors installed along the slope, UGT, watermark, and the corresponding data logger. All this data, and from top to the bottom, we have rainfall, soil temperature, matrix action, and volumetric water content collected at 4 different depths, are collected by 3 data loggers wholly, and all the data are remotely transmitted to a platform that Society ITT Solutions set up ad hoc to visualize on time the measurements. And here there is an example of time series of volumetric water content and soil temperature. So let's move to numerical modeling. The tools used are very simple because we have used SIP W and Slope W in GeoStudio Code. The longitudinal section carried out by stratigraphic logs is modeled, and a mesh with element size of 2.5 centimeter of topsoil and 5 centimeter for the rest of the cover is adopted. About the initial condition, field suction measured 2 days before or 1 day before, depending on the rainfall forecast applied to the upper boundary, are used as initial conditions. About the boundary condition at the the lateral and lower boundaries, the potential phase seepage are used. This means that the water flow flux is null until the pore water pressure are negative. When pore water pressure would become positive, the codes impose null pore pressure and the water flow is free to be disposed through the boundary. At the upper boundary, rainfall forecast 2 days or 1 day before from 3B Meteo, less potential evapotranspiration estimated as function of our temperature forecast today or 1 day before is applied. Before using this model to predict the hydraulic slope behavior, several numeric analyses were carried out to validate this model. But sorry, probably okay, I haven't commented these slides. About hydraulic characterization, on the left there are the soil water retention curves indicated with solid lines. These curves were obtained by interpolating a couple of measurements of matrix action and volumetric water content via Wang HKUST model equation. About hydraulic conductivity, these curves are shown on the right, and these curves were obtained from soil water retention curves and by using the saturated hydraulic conductivity measured for the layers modeled. But for the topsoil, the saturated hydraulic conductivity was assigned as calibration parameters because it affects a lot the good performance of the model. So let's go to the validation of the model. So all these analyses were devoted to find the value to assign to saturated permeability of topsoil to improve the performance of the model in the prediction of field measurements. This value resulted equal to 10 raised to minus 6 meters per second. This value agrees with the values found by other authors that studied the similar soils. So in these slides, the measured matrix action are plotted against the calculated value at the 4 different depths. E is defined as the error, so the difference trivially between the matrix action measured and the matrix action calculated. So E is on average 1 kilopascal. So this result is encouraging, but the bias is 1.23 at the topsoil. So it's high. It's the same for the volumetric water content, because if we look at these slides, measured volumetric water content is plotted against the calculated values again. E is around 0.015, the bias is 0.01. This result suggests to us that we have to increase probably the number of instruments in the first meter of the cover that we are monitoring. So after validated the model, it is used to predict the hydraulic slope behavior under rainfall forecast determined by 3B Meteo. All the hydraulic variables obtained are uploaded in Slope WG Studio, where slip surface are fixed and entry and exit range of slip surfaces are fixed in advance. The minimum slip depth is fixed at 0.5 meters to avoid local failure. and the formulation of Vanapalli is used for soil shear strength to take into account the partial saturation, so the contribute of apparent cohesion. So now I will show the first results of use of this approach. In particular, we start to run this model on May 2022. Now we will show the prediction of the model under 3 rainfall events registered at the test site during autumn. The first event was 25 and 26 September. 52 and 42 millimeter fell respectively on 25 and 26. 1 day before, civil protection emanated the 3rd level of alert, and we can start to say that 3B Meteo underestimated the total daily rainfall 2 days before by 70%, 1 day before by 25%. So now, if we look at the left, we have from top to the bottom, volumetric water content and suction measured and calculated. In particular, the solid lines represent the measurements, the crossed lines represent the results of the model. The third chart reports the factor of safety determined in slope W with indication of the critical slip surface. So, not the critical, I mean the slip surface associated to the minimum value of the safety factor. So we can see that the model seems to work well because field measurements are quite in agreement with the measurements, because these results of the model are carried out by applying the rain gauge rainfall, so the rainfall registered at the test site. In particular, this intense rainfall of September saturated half parts of the cover, and the safety factor went from 6 to 1.64. If we look on the right, we have the same charts, but the solid lines, the crossed lines represent the prediction of the model and the rainfall forecast today before, obtained by 3B Meteo. The situation is not good because the numerical model does predict well the measurements. In particular, suction is positive at the first half part of the cover. This reflects in safety factor that is very high because it's 3.21. But if we apply rainfall forecast 1 day before to the upper boundary of the model, the situation of course improves because the model can reproduce very well the measurement at field. The suction vanished in the first half part of the cover. In fact, safety factor is more close to the reference value of 1.64. Of course, safety factor continues to be overestimated because of bad prediction of early rainfall, because the peak in early rainfall is the real peak in early rainfall is 14 millimeter, but 1 day before, 3B Meteo predicted 8 millimeter. Then let's go to the second event. The second event was on 4 and 5 November, 32 and 42 millimeter fell on 4 and 5 respectively, and civil protection in Campania region emanated the second level of alert. Once again, 3B Meteo underestimated the rainfall either 2 days before and 1 day before. 1 day before by 30% more or less. If you will look on the left, again we have volumetric water content is suction measured and calculated by the model under rain gauge rainfall, so measured at site. The third charts report the factor of safety determined in slope with the indication of slip surface with the corresponding to minimum safety factor. The model continues to work well because is able to reproduce the fully saturation about of the first meter of the cover. The minimum value of safety factor was 2 about. If we look to the result, if we apply rainfall forecast today before, once again the model doesn't work well. In fact, is not able to reproduce the fully saturation of the cover, and safety factor is 3.3, much higher than the reference one. But if we apply the rainfall predict 1 day before, trivially the situation is better, and the safety factor becomes more close to 2 because it's 2.3. But again, it is overestimated because the error of the prediction of rainfall. The last event is very intensive because 100 millimeter fell on 22 November, and civil protection emanate again the third level of alert. This event is very interesting for us because its value is the typical rainfall that triggers the flow-like landslides in our region. Anyway, once again, Trebi Meteo underestimated the rainfall on 22 1 day before by 30% more or less. If you will look on the left, we can see the performance of the model under rain gauge rainfall. We can see that this time the model doesn't work very well at the bottom because volumetric water content is at the bottom is not reproduced very well. At the bottom, I mean at 1 meter, 0.25 meters on reformed soil surface. Anyway, this intense event caused a minimum safety factor of 1.07. If we look to the predictions of the model under rainfall forecast 1 day before, we can see that the model gives back more or less the same results of the previous one. So matrix action and volumetric water content simulated by the model are very similar to the previous one under rain gauge rainfall. In fact, safety factor is 1.1, is very close to the reference value, even if the rainfall is underestimated by 33%. These things can be explained. We can explain this different behavior of a third event respect to other two events in this way. The first things in the third event, there is the error of the model to reproduce the field measurements. The second thing is the initial condition, because for the third event, the initial condition in terms of suction is 30 kilopascal, that is lower, much lower than 100 or 200 kilopascal that established in the cover before the other two events. So probably the rule of initial condition weight more than the discrepancies inside the prediction of rainfall. So the difference between the real rainfall and this predicted 1 day before. So last here, I have plotted on the left the rain gauge rainfall, hourly rain gauge rainfall against the hourly rainfall predicted by Trebi Meteo 1 day before. It is evident that for all these three events, 3B Meteo underestimates rainfall by 33%. This situation reflects to safety factor. It is overestimated. In fact, the difference it is around 0.3, at least for the first two events. For the third event, the situation changes because the safety factor, even if the rainfall predicted one day before and the real one is different, the safety factor predicted by the model is very close to reference one. Probably this is related to the different initial condition that weight more than the discrepancies in the rainfall. Anyway, we have to go in deep in this. But now, to date, we have not conclusion about this work, but we have understood at least some improvements that we have to do to this approach. The first things, we have to install more instrument in the first meter of the cover just to improve the performance of the model. The second, it's very essential, we have better understood the limitation of rain forecasting methods, and at least we have studied the effects of error in rainfall forecast on slope safety factor with the parametrical analysis. So thank you for your attention. I have finished.
Thank you very much, Marianna. We will move on to the next speaker, Marius.
Hi, hello everyone. Let me share my screen. Is my presentation visible, my slides?
Yes.
Yes, thank you very much. So firstly, let me comment the very successful turnout of this workshop. So congratulations to the organizers. And I am Marios Angelopoulos. I'm an associate professor in network and sensing systems at Bournemouth University. And I am going to present lessons learned from a nationally funded project that we run here in the UK. And this is in the context of a line of research that has been being conducted in close collaboration with the British Geological Survey, in particular Catherine Pennington and her landslide team at BGS. But somehow by discussing this use case and lessons learned, I will also be implicitly addressing another cutting research question that we've been working on with Kath and her team. That is it possible to conduct science, to do science by using consumer-graded electronics, which somehow would provide a new angle, a new set of tools in conducting earth science. So let me first talk a bit about the project. So 5G Rural Dorset was a project funded by the UK government and in particular the Department of Culture, Media and Sport under the 5G Testbeds and Trials program. It had a total budget of 9 million, half of which were provided by the government and the rest were by means of own contribution, mainly from the industry. And the remit of the project was to study and actually try to prove that the deployment of 5G networks in rural areas can support sustainable use cases in terms of fiscal or financial viability. And this project was the following. Usually when we're discussing next generation networks such as 5G and 6G networks, this is done in the context of urban environments and urban use cases, smart buildings, smart cities, and so on. However, there's not much discussion about the deployment of these devices in rural settings and how these technologies can help develop use cases that actually underpin growth and the well-being of local communities in these settings. And the underlying issue here is that typically rural settings, in rural areas, the population is very sparsely sparse to the extent that the client base is rather thin, and therefore the financial incentive for mobile network operators to go and deploy communicating infrastructure in these areas is not so strong. So in the context of this project, the aim was firstly to trial 5G technologies in rural settings, secondly to trial novel business and operation models such as neutral hosting and spectrum sharing, and finally to showcase the financial viability of these use cases, and therefore that it is worth to deploy these technologies in rural areas. So in this context, the consortium brought together a diverse set of stakeholders. It was led by Dorset Council, the local authority in the area of Dorset. The technical lead was Satellite Applications Catapult, which is a UK government agency with a strong focus on innovation. We had national authorities such as British Geological Survey, Vodafone, and Neutral Networks were industrial partners with a national scope. There were also partners from the industry that are local stakeholders in the area of Dorset, such as Telint and Accelerate, and of course 2 universities, Bournemouth University and the University of Strathclyde. So the consortium somehow reflects the wide and diverse set of stakeholders who would actually benefit and help deploy these technologies to the benefit of the local communities. So the aim of the project was delivered by means of developing 5 use cases. These covered areas from smart agriculture and future of food to developing commercial activities in the area of Dorset, as well as delivering use cases about safety and coastal management, such as the connected coast and the coastal cliff monitoring. So Work Package X was aimed at developing technical solutions, 5G solutions for coastal cliff monitoring. It is a very relevant use case in the area of Dorset. So for those who are not familiar, Dorset is a county that is located in the south coast of the UK. It is home to the famous Jurassic Coast, and it is predominantly a rural area with beautiful landscapes and very picturesque villages and towns. And it has a coastline that is characterized by coastal cliffs that overlook the beach and the beach walks of Dorset that attract more than a very significant number of tourists. More than 20 million people visit Dorset Coast every year. And this coastal front is very prone to erosion and to landslides, and this issue is aggravated by the ongoing climate crisis, and this poses significant challenges to the local communities that affect not only the management of the natural environment, but also put risks in local communities by means of threatening public infrastructure, property, and so on. And unfortunately, in some cases, even claiming human lives. There was an incident in 2012 that resulted to the death of a person. And the way this happens is the following. So this is Barton Bradstock Beach in Dorset. As you can see, these are the overlooking cliffs that look over the beach. And anytime a landslide takes place, usually the mechanism here is that the sea erodes the foot of the cliff, which leads to unsupported segments of the cliff that eventually collapse. And several fossils are revealed, and there are many fossil hunters who gather after an incident like that. They try to find fossils, and usually there is also a subsequent event that may result to actually harming or even to injuring people. And so this has to do with mainly tourists and local people enjoying the beach. But apart from that, there is also an issue of threatening the local communities. So this is the town of Lyme Regis, again in Dorset, where the nearby cliff, there's a landslide that is ongoing, and it has started claiming parts of the town as well. And this has led to the local authorities building a seawall, a multi-million seawall, in order to try and defend the corresponding section, which, however, has changed the geodynamics of the area, building back pressure, leading to overflanking, to outflanking phenomena, accelerating erosion in other sections of the beach. So this means that for the local communities managing this coastal line not only puts risks, but also demands great amount of resources in order to efficiently manage these areas. So the proposal, our proposal was to develop an IoT-enabled sensor network that would comprise multiple IoT devices that would be very small in their physical form factor, very cheap to develop, and very easy to deploy. That would actively monitor several modalities that pertain to the evolution of the physical phenomenon. These corresponding data would be transmitted using IoT technologies via the network to a backend where data analytics and machine learning algorithms would be deployed in order to try to infer knowledge about the phenomenon, whether it is trying to predict or whether it is actively collecting data that would inform the coastal management plan. Now, this architecture one could claim that this is a very typical architecture comprising the devices wirelessly transmitting data that are collected in a backend for further processing. However, as I will discuss in the following, there are several practicalities hidden that make the deployment of such a system a bit challenging, because the aim, as I mentioned earlier in my subtitle, is to have an operable system that collects data in a way that allows us to do science. That is, the data needs to be calibrated. We need to make sure that the system reports accurate data with the required precision. Another disclaimer here is that the aim was not to develop a system that would replace already existing monitoring methods and instruments, but to actually provide an alternative that would be very easy to deploy, cost-effective. It would alleviate the pressure from local communities in terms of resources on how to continually monitor the areas in question. So in this work was led by University, this geological survey. Vodafone was the mobile network operator who provided the communicating technology, as well as the base chipset around which the devices would be deployed. And of course, other stakeholders like Dorset Council and Neutral Networks were also contributing to this work. So this line of work already spans around 3 or 4 years. So we didn't start from scratch in the context of this project of 5G Rural Dorset. Before that, there were previous iterations. With the main aim was to take an incremental approach in order to have control and make first baby steps, solid baby steps, on top of which we would be able to move to the next level. So the first aim was to investigate the development of devices that would have certain characteristics. So we wanted to have devices that would be rather small and cheap. And in order to do that, we leveraged recent advancements in the areas of electronics, of microcontrollers, and of wireless communication. So for the first iteration, our first approach in designing such a sensing device was to use this chipset, SAMD21 by SparkFun. Now, for those, I appreciate the fact that some of you may not be familiar with. So there is a difference between single board computers, such as the Raspberry Pi, and microcontroller boards. And the main difference is that a single board computer is, as the term implies, it's a computer, miniaturized, yes, and embedded on a single board, but these devices feature fully fledged operating systems, so they run a very lightweight version of a full stack operating system. They have significant compute and networking capabilities. So typically, for instance, a Raspberry Pi features a multi-core processor. It has multiple networking interfaces, and this results in this embedded system actually being quite energy hungry, let's say. It consumes significant amounts of energy, and they typically require a stable source of power, right? So a typical Raspberry Pi cannot be a battery-operated device, or if it is a battery-operated device, the battery needs to be a 12-volt battery that has significant capacity. In contrast, the microprocessors we used for this line of work, they're ultra low power. They can be powered by simple AA, AAA batteries or coin cell batteries. They are very restricted in terms of the resources and the capabilities, the compute and networking capabilities they support. So this means that the corresponding firmware requires special suits. Some of you may already be familiar with the Arduino platform, which is used by enthusiasts and hobbyists in order to develop home projects. But this brings us back to the underlying research question, whether these consumer-graded electronics that are ultra cheap, ultra low, and they are not graded for scientific or industrial use, can we use these platforms in order to develop a monitoring system that can be used in order to somehow help manage public safety and monitor scientifically such phenomena. So our first approach was this device. It featured a geophone and a GPS RTK2 board in order to monitor soil displacement, and the electronics were configured in such a way that the device would enter very deep sleep cycles for extended amounts of time, so thus saving a lot on energy consumption. And when the geophone was detecting a significant signal that would be deemed to be a potential precursor to an incident, then this would wake up the main board that would enter an active sensing cycle. So we did a careful desktop evaluation of the design by using simple D-cell batteries of 8,400 milliamps. We analyzed the state diagram of the software that was developed, of the firmware that was developed for this device, and we came up an estimation that the device would be able to operate on 3-hour cycles. That is, the device would be able to report sensing data every 3 hours for around something little less than 2 years period of time. So the devices, three devices were developed, and they were deployed at a landslide site that is located within the urban area of Bournemouth. As I said, the first aim was to establish the basics of the design. So the devices were able to operate continuously for over a year. There were some data captured, but these data were uncalibrated, and therefore we weren't able to use those in order to infer some insights on how the landslide behaved. By uncalibrated data, I mean that we're using over-the-shelf components of components, of hardware components that are very low cost, and therefore their sensitivity and precision depend on the particular setup that they are being used, and also the context. So this highlighted the need in order to firstly conduct studies under controlled environment in order to establish the precision and the accuracy and the other characteristics of the sensors in order to collect data that would actually be useful from a scientific perspective. However, there were also some positive lessons learned. The design of the device, the physical design, demonstrated good resilience against weather elements and corrosion. And another interesting practicality that was brought to our attention from this first pilot is that the devices attracted attention from wildlife. So the casings we used were white or light gray, and this stood out against the brown background of the cliff. And because the area is by the sea, there were several seagulls that were actually trying to pick the devices, and this resulted in weird spikes appearing in the collected data. So when we're discussing about deploying such a system in a natural environment, these are aspects that need to also be taken into consideration. Now coming back to work conducted in the context of the 5G Rural Dorset project, it became immediately apparent that there was this is a highly interdisciplinary line of work, and there was a language gap that we needed to bridge between academics in the area of computer science, scientists in the area of earth science, and people from the industry who are coming from a totally different background. They're with the main aim on the aim and focus on the technology. So BGS hosted a series of workshops that with the aim of actually trying to bridge this language gap. On one hand, the geologists weren't quite sure of the capabilities of the technology. On the other side, people from the industry and people from computer science were not sure what the technical aspects of earth science would be relevant. And as a result of these workshops, we agreed on a set of modalities and that would be of interest with respect to coastal landslides. And we tried to scope the market in order to identify corresponding components that would be useful in this context. So we considered ultrasonic ranges, time of flight mini LiDAR sensors, time-of-flight laser distance sensors, digital gyroscopes, 6-axis, digital accelerometers, compass altimeters, barometric pressure, rugged soil moisture, and so on. And we changed the development platform to the universal prototyper board provided by Vodafone. You can see that the actual size of the board is very, very small. It's comparable to that of a small matchbox. And you can see here a typical 3000 milliampere hour battery. And this gives you a good impression of how small the board is. It measures like 2 or 3 centimeters on each edge. So this is a board developed by Vodafone, and it features an eSIM with over-the-air programming support. And the design aim of the board is to provide more than 10 years battery lifetime. So this device was supposed to be part of the 5G Vodafone network and to operate seamlessly. So as far as we were concerned, this was part of a black box, of a black pipeline, where the device would be interfaced with our sensors. It would transmit data over the 5G network of Vodafone, and Vodafone would expose this data to the other side over programmable interfaces that would allow an external application server to pull the data and store them for further processing. We experimented with the physical design of the devices. So this picture depicts the first set of devices. You can see this tiny hole here is the laser time-of-flight sensor. This is the ultrasonic time-of-flight sensor, and this is the LiDAR time-of-flight sensors, who are used in order to measure distances. So one application BGS suggested was that we could instrument existing boreholes that monitor underground water levels with such ranging devices in order to remotely be able to monitor the level of the underground water. We also experimented with using PV panels, small PV panels, in order to harvest solar energy. This was not very successful. Nevertheless, it provided useful insights in order to further improve the physical design of the devices. And these are 2 other examples of devices we developed. So the devices were deployed, and there were some significant lessons learned. The first thing is that when we're discussing about deploying sensing systems in a natural environment, we need to be aware of and adhere to local legislation. So, for instance, in the Dorset area, in the Jurassic Coast, there are several sites that are of special scientific interest. And there is a regulation on how one can access these sites and what instruments can deploy. So in our case, we needed to conduct an ecological watch survey in order to make sure that the disturbance to the natural environment is minimized as much as possible, and that it doesn't pose any risk to local wildlife and plants. And this led to have a very specific window of deployment in order to avoid bird nesting season in the area. So in streamlining the deployment of such systems, these are important considerations. The design, again, was proven resilient against weather conditions. However, because these are coastal sites, sea salt corrosion can affect performance. So this also is a consideration that needs to be taken into account. Now, thick vegetation and terrain affect connectivity in rural areas. Professor Wang in the beginning mentioned that in the Hong Kong area, there are no hills or mountains, but there is a very rich and high skyline in the area with big buildings. Interestingly enough, in urban environment where the surfaces are flat or sharp, so we can have big glass panels in the area, they may have a counterintuitive effect of actually facilitating wireless connectivity by providing multipath propagation by means of having the wireless signal reflect on these devices. However, in a natural environment, this is not the case. Actually, it is one of the harshest wireless communicating, harshest environments for wireless communications. It also varies. The environment changes over the course of a year with the fauna changing depending on the season. As I mentioned earlier, typically in rural environments, the communication infrastructure is deployed in a much more sparse way. So the average distance to the local cell tower, for instance, in the context of 5G, can be significantly longer than that in an urban environment. Another point is that we need to be aware of the potential environmental impact of equipment and materials. For instance, in a landslide, particularly in phenomena like a landslide, we can expect the devices to actually be washed away and therefore be non-retrievable. To be, for instance, in a coastal landslide, they may be washed away in the ocean. So we need to take into consideration what material we're using. So, for instance, what types of batteries we're using. Another lesson learned is the security against wildlife, as well as the public. In such areas, for instance, in our areas of deployment, the areas were publicly accessible. So there was also a question on whether people will try to nick the devices or whether they will try to fiddle with them and play around. But while this can be seen as a risk to the system, we can actually use this as an opportunity to engage with the public. So instead of trying to hide the devices away from the public side, perhaps we can actually inform the public of their presence and therefore create the sense to the public that this is a monitored area because it is a site of special scientific interest, or we're monitoring this area in order to manage the risks and so on. Therefore, we can use the deployment of such systems as a means of communicating and engaging with the public. There were some negative lessons learned. So the system, while it was successful in validating the design and the development of the devices, there were issues that emerged with respect to the 5G technology and the deployment of the wireless communicating device technologies in rural areas. There were several technical issues that emerged. I'm not going to delve into these now, but if one is interested, I'm happy to answer a follow-up question on that. So from a technical perspective, the technologies are still evolving. This is a very this is a landscape, a technological landscape that evolves at a rapid pace. However, advancements are being made, and we already see such technologies being deployed commercially. So what are the future extensions? As I mentioned, this is a line of work that takes an iterative approach in making progress. So now that we have the design of the systems, the design of the devices established, we are aware of the processes and of the aspects of how one can deploy and operate such a system in a rural setting. We have two follow-up projects. The first one is a PhD project in collaboration with the British Geological Survey and Dorset Council that will aim at employing machine learning and AI technologies in conjunction with IoT technologies. So I believe it was Luca at the very beginning this morning who posed the question of what is IoT, Internet of Things. I would say I would try to define it somehow, to outline the paradigm of IoT by somehow saying what it is not, according to my view. So IoT is something that is beyond the narrow scope of remotely collecting and transmitting data. This could be classified as telemetry, and we've been able to remotely transmit data wirelessly since many decades. However, IoT is about enabling embedded devices to actually use wireless connecting networking technologies, let's say, broadly speaking, the internet, for the same reason that people do, in order to generate data and information and exchange data and information among them. So in that sense, we will look at employing AI and machine learning methods in order to infer knowledge from collected sensory data. But then we will also look at deploying such methods natively on the IoT device. So the vision is that the IoT device, the sensing device, will not simply transmit raw streams of data to the backend, but will be able to locally process this data on the device and then report back on information at a higher, more abstract domain. So, for instance, whether there is some soil displacement and so on. This will enable to have a much shorter response time for the system, and will also facilitate the task of actually interpreting the data. Rather than having to navigate ourselves in big volumes of raw signals, the aim will be for the devices to report on events. Another important aspect with respect to the use of machine learning and AI technologies is to have explainable models. For those perhaps not familiar, we've been listening the discussions about deep learning and neural networks. The way these models, these techniques work is that we'll allow several layers of the model to actually self-configure and change the configuration of themselves, but this happens in an automated way and in somehow an uncontrollable way. So this leads to the predicament that we're not fully aware of how an AI model actually reaches the conclusion, or how it actually processes the information in order to give the output it gives. So an important aspect is to have explainable AI. So when we have a model that, based on some input signals, is able to infer whether there is an imminent landslide, let's say, or what the likelihood of an imminent landslide is, we want to be able to reason on what were the steps for this model to reach this conclusion. And by gaining such insights, it will allow us to actually refine the models we have for landslides. Other aspects include digital twins for the natural environment. Yes, I know, I'm aware. So just
1 minute.
Yes, I'm about to conclude. So the last mention is about the HAT project. This is an ongoing European project. BGS is also a partner to this consortium. Bournemouth University is subcontracted, and this has to do about the use of developing several demonstrators in order to see how the extreme climate change affects people and how we can better manage that. So that is my talk. Thank you very much. Happy to receive any questions.
Okay, thank you very much. That was very interesting, Marius. And thank you again to all 4 of our speakers. I think we're going to hand it off to Luca, and we'll pull up all 4 speakers. If you could please turn your cameras back on. We'll open the floor to questions and discussion, and Luca will moderate.
Yes. Okay. So I think now it's the one of the most important moments, I would say, where we can share experiences and we can make questions first to the speakers, and then we can comment and have a short discussion. So I really like that Zhongqiang has set like a good amount of time for this part of the workshop. And I would start with questions for the speakers. So from the audience, do you have questions for the speakers? If yes, please turn your camera on and your mic on, and then just make the question. No question from the audience? I can start. I know that at the beginning is always a little bit like that, but I can start asking a curiosity, a question to Marianna with the sensors that they have used. I agree that calibration of the sensors is important, and I was curious because maybe I didn't get what type of sensors have you used for the suction, and if these sensors was in real time monitored or was just going there and collect the data. Yeah.
Okay, thank you for your question, Luca. Just because I have the opportunity to specify, to clarify this sensor that I installed. About matrix suction, we installed the traditional tensiometers that we have used as reference. Then we have installed watermark sensors. These sensors, we have calibrated this sensor at laboratory. In particular, we put this sensor in the sample, the same soil that we collected at site. In that sample, we put with the watermark sensor and a small tip tensiometer, and also a Decagorn sensor, just to follow the measurement, also the volumetric water content. So we obtained the calibration by drying and imbibition of this soil sample at laboratory. And to be honest, it was very hard, because this sensor depends a lot of temperature. So when we have to purchase other sensor of this type, it's important to associate a compensator of temperature, because depends a lot. The measure oscillates. So just about this issue, I had a question for Emir, because I'm very curious about your experience about the meter sensor for measuring water content, because I think that the technology is the same, but I'm curious to know about your experience about it. So yes, okay. The calibration was very hard about the watermark sensors, and so I suggest, of course, to install them below 50 centimeters, just to avoid the effects of soil temperature and air temperature. And then the other question was about, the transmission. The field data are collected orally and are transmitted online. So it's possible to visualize also now the measurements, thanks to the platform that ETT Society carried out.
Thanks, Marianna. Before Emir to reply to your question,
and I have also one question. So yeah,
I have no experience with this watermark soil sensor. I was just Googling it, but this is for soil moisture, right? I was written soil moisture. I was speaking about suction. It's your.
I guess. Okay. So no, watermark sensor, it's you say right, because this sensor measure the electrical properties of the porous stone that represent the reference sensor. So these electrical properties are related to the water content of the porous stone. So matrix action is inferred from the water content of the porous stone. So it's like very important to have the water retention curve of the porous stone.
So it's like the Teros 21, it's exactly the same, which is through the porous media. And in that case, it's, yeah, I agree, it's very important to so you have built the Wang HKUST water retention curve yourself, that you have assigned.
Yes.
You have used your own curves, which is the best way of using these type of sensors like Teros 21, like this one and others. And actually, mentioning the temperature effects, I have seen in your graphs that for shallow sensors, you may see a lot of waves.
Right.
And that's due to the temperature. Yeah.
So
yes.
For this reason, I have asked the question about the Teros, because I'm curious about it.
Yeah, thank you. So, thank you, Marianna. So, regarding my work, also Luca's work currently has this Teros 21 from Meter Group, which, as I understood, has the same principle as watermark that you have used with porous stones, and they have certain soil water characteristics curve, and depending on the water content in those porous stones, you calculate the suction value. So I also used it. I also calibrated it in the laboratory with the soil type that I have in the field with the same porosity and density, etc. And I also generated my own SWCC curve, Wangen chain characteristics, and so on. With respect to reliability of that sensor, so for example, when I use the data that I have from the field, I couldn't really have a nice SWCC because I just used drying part of the data. When you take the wetting part of the data, the response time of volumetric water content and suction sensors are not the same. Volumetric water content from Meter Group was quite satisfactory for me. So also from the laboratory experiments, it was quite okay. But the suction sensors take some time until it calibrates. It came into equilibrium. Then when you pair the readings, then you see jumps and like goes down, up. So, and it just ruins the data or the data set that you have. Then we decided to remove it. That also Luca contacted Meter Group to see if we can fix this problem somehow, or if we have certain delay in the response, maybe we can just adjust somehow. But yeah, it didn't work out as I understood. So
we haven't received any reply, and they were also reluctant to explicitly say that the suction that you were measuring with the Teros 21 was not the suction of the soil, but was the suction of the porous media, because the porous media has its own soil water retention curve. So this is what you are measuring if you use this sensor with the porous media to measure suction.
And if you wait enough until it gets into equilibrium, then it should be the same suction at the surrounding soil, but we don't have that much time. So therefore I was considering like micro electromechanical sensors that like Yu-Hsing Wang, Professor Wang mentioned. So we need some other type of sensors in this work, in my opinion, just to have more reliable data with respect to suction, in my opinion.
Thank you. Thank you.
Yeah, Dylan, go ahead.
Yeah, I have a question maybe for all the speakers. Marianna showed nicely that it's actually the initial conditions were very important for the predictive capability. And I assume that's the case for a physics-based model, but also probably something that's based on machine learning. But then we also had people showing that in order to improve the lifetime by reducing power consumption, they're adding mechanical sensors maybe, or some way to trigger to turn these systems on so that they start recording. And so I'm just very curious from a philosophical point of view, if we want to make something that lasts for 10 years, that can continuously be used in a predictive way. How do we do that? Because Marius showed that they had a geophone hooked up to their sensor that when it felt some vibrations, it turned on and started logging or transmitting data. But Marianna showed that we need the real-time data to do the initial conditions. So how do we deal with these two wishes? One for long-term battery life, but then also continuous recording.
Yeah, from my study, I can just briefly explain. Like we were collecting data every 15 minutes or 10 minutes, and we were sending it from the IoT box to the cloud system every 1 hour. As Marius showed, also our system sleeps and waits in between those 10 minutes. So if something happens in that 10 minutes, of course, we will not be able to capture it. But this is rainfall-induced landslides, so we were not really expecting something very sudden appear. So it just builds up by time. So it also depends on the failure mechanism that you have. So if it is sudden or not. So we were mainly focusing on rainfall-induced landslides.
So I'm not sure if I have understood very well the questions, but I try to reply to you. So our approach consists of measuring on time hourly the field suction and field water content. So each day we can see these measurements, and each day we can run the model by applying to upper boundary rainfall forecast, for example, 1 day before. So 24 hours in advance, we can have the information, we can have an idea about what can happen the following day. So we can try to forecast the flow like landslides 1 day before or 2 days before. But I don't believe in 2 days before, but more in 1 day before.
Great, thanks.
I don't know if I have replied to your curiosity or question.
Yeah, you do. And I think Emir points also a good point. It depends on what you're trying to look at and how often you need to send data. But I would be curious to hear from the other two speakers as well, their thoughts.
Yeah, maybe can I share a little bit of my experience? I know, right? Every time we look at sensor design, we know what we want to measure. So we know the power supply. We also know the limitation for power supply. We also know the power consumption. So, for example, we try to minimize the energy consumption. But in the meantime, I want to provide another angle to look at this issue. We do the energy harvesting. So we put a solar panel directly on the sensor box. And because solar panel now is you can find a more advanced one, very flexible and thin, like a credit card, and quite powerful. So just one, and then we also have you can think about other methods for the energy harvesting, because it's always quite difficult. You decide when the sensor needs to go to sleep. Even the sensor is sleeping, it still consumes energy because the clock still clicking. So of course, we need to optimize our design, but in the meantime, we can be more proactive to get the energy. Yeah, that's what I want to answer.
If I could share my insight, I believe that the question pertains to, firstly, the technology available. So already in the past 10 years, they have been made, leaps forward have been made in the area of low power electronics. And this also pertains to the requirements, to the functional requirements of the application. So as a computer engineer, from my end, a question I would pose is what are the requirements in order to efficiently and effectively be able to monitor I dare say, predict, or I don't know if this is like the correct approach, a physical phenomenon. So what would be the sampling rate? How dense would we like the data to be, both in the time domain as well as in the space domain? So, for instance, if we were able to monitor underground water levels every couple of hours per day, or once or twice per day, that can greatly affect the lifetime, the battery lifetime of the system. Professor Wang is right to say that there are ways that we can alleviate this problem with energy harvesting. However, we need to also take into account the environment of operation. So, for instance, solar panels can be a good idea for an urban environment, but in a natural environment with fauna growing around, dirt and salt accumulating on the surface of the panel, and the device is typically being deployed in areas that are not easily accessible, can this be a viable solution? Some other researchers, I'm aware, they're trialing, for instance, wind harvesting, with having very tiny miniature windmills on the devices. Other techniques come from backscattering, meaning that the devices carry special circuits that are able to harvest energy from ambient electromagnetic fields that already either way exist somewhere. But I would say that the predominant factor is specifying the functional requirements of the operation. How quickly, how frequent, how much data do we need in the context of an operation, of a deployment.
Okay, thank you. I see Michaela has his hand up.
Can you hear me?
Yes.
Okay, thank you very much. First of all, congratulations to all the speakers, also to the organizers for the very interesting workshop. So very interesting presentations and a lot of food for thought. A very specific and curiosity question for Marius. You were mentioning, your cooperation with Vodafone, and at some point you mentioned this Vodafone Universal Prototyper Evaluation Board. What is that exactly? Is it something that it's already commercially available? But I didn't understand exactly where it fits in the process from the sensing to the... Okay, anyway, that's my question.
Absolutely. So in order to develop such an embedded device, an IoT device, we need a development platform. That would say, for instance, in terms of a regular computer, we would need a motherboard, on top of which several peripherals they are put on. It's not exactly the same thing, it's just an analogy. So the Universal Prototyper Board is a development platform that is developed in-house by Vodafone. So we don't have details, exact details on on the design of the board. And it is designed, the intention was to be seamlessly integrated to the Vodafone network. So it's just, you deploy and it plays. However, this is at the development phases. Essentially, the use case somehow played the role of the alpha tester for Vodafone for this device. And this is why we had these hiccups with how the device eventually operated in terms of energy efficiency, in terms of actually being able to log into the Vodafone network and transmit the data. As far as the overarching application area is concerned, landslide monitoring and so on, this is just a module that we can replace with, let's say, an Arduino board. Because from the context of the application, the focus is on the modalities we're sensing and how we transmit corresponding data back to the backend for further processing. So instead of having, let's say, one type of microprocessor, we can have a different type of microprocessor that will affect the design of the device. Therefore, this is a subject of study from my discipline. But as far as the application, the overarching application is concerned, this is just a module that we can exchange, we can change seamlessly.
Yeah, thanks. Thank you, Marius. Other questions from the audience? Marianna, yeah.
Yes, I have two questions for Emir. Emir, okay, your monitoring is very interesting. So just two curiosities. The first one is about the number of sensors that you installed. I have seen that the last sensor was at 0.9 meter from soil level, or
Yes.
I'm
Yeah,
wrong?
No,
Yes.
this is correct. So the suction and volumetric water content pair, the deepest is 0.9 meter depth.
Because the thickness of the cover is 1 meter, or because there is a water table? Why this?
At one location monitoring point, the depth to bedrock was 1 meter, 1 to 1.5 meter depth. For the other one, it was deeper, but still we decided to just investigate the very shallow part of the soil. So, and we did it ourselves, so it will be quite tough to install them at a deeper depth. So.
Yes, I know. And so about the lower boundary of the cover, have you any information? So I don't know, the interaction between your cover with bedrock is fracturated, is not fracturated?
Yeah, no, at one monitoring point, it was quite obvious that the bedrock affects the volumetric water content readings, because the rainfall start accumulating at the bedrock, and we see a jump in the volumetric water content readings at the deepest at one monitoring point, while the other monitoring points doesn't show that. It was purely because of the bedrock being at 1 meter depth. So we decided to place the sensors in a way that we can capture all different things, mechanism. Also, it's quite important to investigate the three-dimensional effects of the valley, like the flow of water in 2 dimensions and so on. We also made some interpretations on that, but we couldn't conclude it, so it requires more investigation in that.
So thank you a lot.
Yeah, you're welcome. Thanks.
I may have a question for all speakers. As Amir pointed out, there are different levels of models. We have data-based models and empirical correlation-based models and physics-based models. I mean, for all these 4 models, 3 models, we have limitations and advantages. For me, I mean, since we have a lot of sensors and we use IoT technique, probably it's more reliable if we can utilize the data-based models. But for instance, Marianna also pointed out there are some uncertainties associated with physical models. So perhaps, I mean, if you have more advanced model, you may introduce more uncertainties. Since we use just measure data, raw data, perhaps we can reduce uncertainty, but the model could be not so reliable or robust. But I just would like to hear what's the opinions from our both speakers. And I noticed perhaps Yu-Hsing and Marios, you are looking into more data-based models, not physical models.
Yeah, Yu-Hsing, what do you want to start replying? You can start in the same order.
Yeah, maybe I can start this.
Yeah.
I think the key point is not about which way you use. The key point is in each way, indeed, we don't have the ability to get all the data we need. So maybe we can start from the numerical simulation. I have a 1 PhD student, we want to do the numerical simulation, and then just think about how much water from the rainfall will go for infiltration instead of the runoff. It's already a very difficult question because you have different vegetation, you have different soil condition, different suction, different antecedent rainfall. They all will change how much water will go infiltrate into your slope. And then you don't know your geological condition. So all the numerical simulation, okay, even we talk about constitutive modeling, we don't have a very good unified considered model. So I think from numerical simulation point of view, we have a lot of limitation there. We want to make a simulation correct, but it's practically impossible because we don't have those parameters. We don't have a good model. And then even though you have good model, but we don't have measurement for those parameters, sometimes the model can be like 15 parameters. Okay, and then come back to the data-driven. Once again, you want to get a very useful data, and however, your measurement is only point. You only get the point data. You don't have the overall pictures. And then a lot of time we use rainfall. But for me, when I start to the project using the sensor, because I would feel rainfall is not direct parameter. It's just a rainfall. I want to get a direct parameter about the slope really move. So I begin to design those sensors. But I also realize you can look at a lot of people using different sensors, measure different things. And they measure the force, they measure pressure, measure suction, measure water content, measure the level of groundwater. So you can see all kinds of measurement. But however, still is a point data. And also it's very expensive. It's not easy. And then you keep it's not cheap at all. So again, those technology limitations will also give us the same unpleasant result is we don't have enough data. So everything is just based on the few point measurement. Yeah, so what is the other one? Okay, I only mentioned two, right? But I think the point is the way it is data-driven, always numerical simulation, we don't have over picture. So we probably need both to help us because we cannot get enough parameter or enough measurement for each one. Yeah, and I forgot the third one. What is the third one for the prediction?
Third way, I think Amir pointed out this empirical correlation based.
Oh, empirical, yeah. Empirical is I always thought, right, you look at geotechnical field, we have so many empirical relationships. And then we give ourselves a very good excuse because it's too complicated. But I always think, right, if you consider the medical area, the human body is even more complicated. But we don't use empirical relationship to to give you treatment, right? This is, of course, we don't have a choice. We use the empirical relationship, but I personally really think, even though we use the empirical relationship, every parameter needs to have physical meaning, but it's hard. But I really think that the technology will lead us to different situation because just think about the suction. I have a crazy idea. Ask my student to change the way we measure suction. Right, you measure SWCC, it takes you months because the equilibrium process, and then you look at a tensiometer, only make it saturate is already very troublesome before you start the measurement. So without changing those technology limitations, you will limit us a lot because we don't have a good sensor, we cannot do the good measurement, and eventually we will be forced to use empirical relationship. So anyway, now we have the free model, but that's what we have. So we probably can use the best of each part and then combine together to have an overall picture about the landslide prediction, etc. Yeah, that's just my personal view.
Yeah, I totally agree with all the points that you made, first of all. So we have quite limited data, limited system technology, but what we do is we just try to do the best possible predictions out of them. So, and I want to point out that we don't always know the problem. So understanding of the problem that we have is also quite crucial when we come to predictions. So sometimes it initiates due to hydrological things, sometimes it is erosion induced, and many other times there are different causes. And when it comes to physical-based models, we have different levels of complexity. There are basic ones, there are very advanced ones, as Yu-Hsing Wang mentioned, like constitutive models, some of them has like 2-3 model parameters, some of them has like 25-30 parameters, some of them have physical meaning, actual meaning, some of them have no meaning at all, except the guy who developed that model. So, but what I believe that when it comes to practical usage, so the simplest is always the best solution. Of course, we should combine the best practice from each of these and combine them in a good way, as Yu-Hsing Wang said. So I don't have anything to add on top of that. So thanks.
So, okay, this is a big problem, and essentially I agree with my colleagues that I have spoken before. So about the prediction, there are a lot of uncertainties that I have mentioned before, but I think that the model prediction can work if we focus at the scale of the slope. In fact, our approach, we think this approach to be effective at that scale, but the key of good working is collecting and wide experience about geotechnical soil characterization of the geomorphological context where the landslides occur. So we have, after a lot of years that we have collected familiarities with this soil, we have tried to simplify the model that can well predict the hydraulic slope behavior. In fact, for this reason, we try to use the simple model as a SIPW, because in our opinion, hydraulic characterization weight a lot. So the key is trivially a good geotechnical soil characterization just at the area where we are seeking to do and to apply this approach. Okay, about empirical rainfall threshold, these curves are used a lot also in Italy. I think that there is a problem of course about false alarms, and I think that it's better to move on physical based rainfall thresholds as an alternative to on-time triggering, just to study a geomorphological context. So it's necessary to avoid to extend at regional scale the empirical rainfall threshold, but also the physical based rainfall threshold. These curves works well at the scale of basin, not over the region. So probably it's important to move in this direction, but this is my opinion, just my opinion.
So perhaps I could also make a last remark on this point. So I can comment on what is the paradigm shift that machine learning and AI bring. So when we're trying to model or to extract models characterizing a process, whether it is natural language modeling or a physical phenomenon, or how light dissipates and illuminates a physical space, there are several approaches. The first approach that has been traditionally being used in science is to elicit numerical models. So, for instance, in terms of natural language, to try and characterize, use the syntax rules and the grammar rules, and then develop a model that will be able to predict the next word in a sentence. In light, for instance, when it comes to light dissemination, we can have ray tracing that is based on physical laws. But this is a very copious task, and that doesn't scale well. It is useful, but doesn't scale well. So other approaches involved stochastic models, developing stochastic models, trying to capture the stochastic attributes of a process. What AI does is that shifts the burden from trying to construct a model, a detailed model, to actually allowing a system to make guesses, and then the person, the human in the loop, actually validates these or rejects these guesses. And via this trial and error process, the model actually learns what the correct answers are in this domain of question. But this now begs the question that we can have a process, a model, making the right corrections without actually having any insight on how it reaches these conclusions. And this brings us back to my comment I made in my talk about explainable models in AI. So essentially, AI can help us alleviate the burden of trying to capture all the details of a particular process in a particular context, but it is not a panacea. It doesn't mean that it negates the need